Hi, this is the first video on the review for the lab final. The lab final is kind of structured where it has questions from the different labs that we did this semester. So the first lab we did was a measurements lab. And again, this final will be online, so it'll be all multiple choice, but some of those multiple choice may require you to do calculations. If you go to Canvas under the module called Lab Final, there should be a review, and that review is pretty accurate except that we didn't do the acid-base lab, so there'll be no questions on acids, bases. And then there should also be a handout that we would have gone over if we'd had a chance to meet together and discuss the lab final. So I'll be working through some of those problems, so what you should probably do is go on Canvas before you start watching this and either print out or open the copy of the handout for the lab final review, because the problems that we will be covering here will be from that review, unless I just spontaneously make up some problems here. So lab one, if you remember, was our lab on measurements. So that was a lab where we learned how to start making scientific measurements. So there'll be questions on the final about how you would make measurements. So what type of equipment would you use if you wanted to weigh the mass of something? What would you use to measure the length of something or the volume? So those are the main measurements we made: mass, length, and volume. So you should be familiar with what lab equipment to use to make those different measurements. Also, there will be safety questions, just like on the midterm. And the safety questions are pretty generic questions, so as long as you're somewhat familiar with lab safety, you should be fine with those questions. Let's see what else from this lab is on there. Significant figures. So again, we've spent a lot of time on significant figures, but remember, if the number is not a zero, then it's significant. So all non-zeros are significant. So, you know, if we had a number like 1, 2, 3, 4, 5. It has 5 numbers. They're all non-zeros, so all of those would be significant, right? So this would have 5 significant figures. If we put some leading zeros out here, leading zeros are never significant. So those zeros at the front don't tell us anything, so that number still has 5 significant figures. We could even put a decimal point in here, but these are still leading zeros, so that number still has 5 significant figures, right? So when we have to make a question about if a zero is significant or not is if it's at the end of a number. So if we put a 0 here, if there's a decimal, it makes zeros at the end of the number significant. So we have 1, 2, 3, 4, 5, 6 significant figures. So make sure you can recognize and count the number of significant figures. If we didn't have this decimal here, right, then this 0 back here doesn't mean anything. This number now is 1, 2, 3, 4, 5, 0, which would only have 5 significant figures. So that decimal, again, makes the zeros at the end significant, but not the ones at the front. The 1 0 we didn't talk about was a trapped 0, and that's a 0 that's between 2 non-zero numbers. So let me quickly throw a trapped 0 in there. So if we put a 7 at the end, this 0 is between 2 non-zeros, so all of these numbers now are significant. So refresh yourself on the rules of significant figure from Lab 1. And the other thing we covered in Lab 1 was density, right? Lab 1 was when we measured those aluminum cylinders and weighed them, so we had their volume and their mass, so then we were able to figure out a density, right? And so remember, density is just the mass divided by the volume. So there were a couple different ways you could see this formula, that density equals mass over volume. And if we have a problem, and this is the problem on the handout, if we have a metal cylinder that has a density of 3.2 grams per milliliter, so those are units of density. It's a mass divided by a volume, and it has a mass of 16.00 grams. And what is the volume? All right, on your sheet you should have the three different density equations. So this is asking for volume, so we need to know that our volume is going to equal our mass divided by our density, right? So when we rearrange that, it's volume over density. And now we have a mass and we have a density, so we'll just plug those in. So we have a mass of 16.00 grams, and we're dividing by 3.2 grams per milliliter. So we're going to plug 16 into our calculator, divide by 3.22, and you get a density of 5.0 milliliters. So make sure you can do from Lab 1 a simple density type problem. All right, so Lab 2 was our states of matter lab, and if you remember, that's the lab where we took the solid water or the ice and we heated it up, converted it to liquid water, and then kept heating that water until it boiled and evaporated and became gas water. Right, so there are a couple of things from Lab 2 you should know. You should know the difference between a chemical change and a physical change. Remember, in a physical change, no new compounds or elements are formed. So in a physical change, we're just usually changing a state of matter, right? If we're melting something, say we took our solid ice and we melted it, it became liquid ice, right? Or liquid water. So you still have the same matter present before and after the change. And we also talked about conservation of mass or matter in that lab, right? So the amount of solid material you had weighed the same as liquid material. In a chemical change, as opposed to that, a new compound has to be formed in a chemical change, right? And so, you know, at this point, we weren't really talking about chemical changes, but chemical changes involve new things being formed. So usually if you see the word oxidized or burned or something like that in a description of what happened, that's usually a chemical change, right? So, you know, if we eat some food and we digest it, then we're converting whatever chemicals were in that food into energy for our body. The other thing we kind of touched on in there that you should know the differences between an element, a compound, and a mixture, right? So an element is any one of those things by itself on the periodic table, right? So if we had an iron bar, and if we look at what iron is, it's the symbol Fe, which is just one of the things on the periodic table, so that's an example of an element, right? If we had something like carbon monoxide, that's a compound. So a compound is when you have at least two different elements combined to make a molecule, right? And we have carbon dioxide down there. So if we look at what the chemical symbol is, now that you know your naming, carbon monoxide is one carbon and one oxygen. So that's a compound because you have two different elements combined. And the other thing is a mixture, right? A mixture is whenever you have multiple elements or compounds together, right? So something like milk is a mixture. You have water in there. You have like fat molecules. You have calcium, other nutrients and vitamins and minerals in there. So, you know, a mixture is, as it sounds, a mix of things. Other thing from Lab 2 we touched on was kinetic theory of matter, right? So you should know matter is made up of these small particles. Now we know they're atoms. The amount of energy these particles have determines the state of matter, right? If we put in more energy, we can convert from one state of matter to another. And that's kind of the third point, is that it actually takes energy to cause these changes in states of matter. So you should be familiar with the three states of matter. You know, what are the properties of a solid, a liquid, and a gas. So remember, a solid has a fixed shape and a fixed volume. And a solid is the lowest energy state, right? The particles in a solid are locked into position and they're not free to move around. They kind of can vibrate in space. Once we get to a liquid, we've put in more energy, and those particles or molecules are still attracted to each other, but now they can kind of flow around each other, and so you get that movement that you see in a liquid. And that's why a liquid still has a fixed volume, because those particles or molecules are still stuck to each other. They're not free just to go wherever they want. They're still stuck to their neighbors, but just a little more loosely stuck. And that's why they take the shape of their container, right? So they can kind of spread out and cover a surface. As we get to the highest state of matter, a gas, that's when there's really no interaction left between the particles or the molecules. They're just flying off wherever they want to go. And so at this point, then you have neither a fixed shape or a fixed volume. All right, so lab 3 was our specific heat or calorimetry lab. Remember, that's a lab where we heated up some metal, dumped it into a little styrofoam cup with some water, measured how much the temperature changed, and then calculated the specific heat of that metal. Right, and there are a couple of concepts in play in this lab. One was conservation of energy. So, right, energy is neither created nor destroyed. It's just transferred from one thing to another. So when we heated up that metal and dropped it into the cooler water, that metal lost energy, and it didn't disappear because we had a closed system. The energy that the metal lost was the energy gained by the water, right? And so that kind of takes us to the next thing we talked about were exothermic changes and endothermic changes. And in an exothermic change, energy is leaving the system, so it's exiting, right? So the metal was undergoing an exothermic change. It was giving away its energy. And endothermic means it's taking in the energy, so the water was taking in the energy. So you should know the difference between exothermic and endothermic. The main thing we did was worked with this equation to find specific heat, right? So the amount of energy, well, specific heat is the amount of energy it takes to change 1 gram of a substance 1 degree Celsius. So we calculated the specific heat, but you should be able to figure out how much energy is required, right? So if something has a high specific heat, it takes more energy to change its temperature. So if we had a problem like this, how much energy is required to change the temperature of 3,999 milliliters of water from 22 degrees to 100 degrees, and it gives us its specific heat. Since it's asking for energy, Q is our unknown, right? So our specific heat is 4.184 joules per gram degree Celsius. Then we need a mass. And here it gives us the mass in milliliters, but we probably may or may not remember, but the density of water is 1 gram per milliliter. So if you have 3,999 milliliters, you also have 3,999 grams. And then we need a change in temperature. And so remember, that's our final temperature minus our initial temperature. So we're starting at 22 degrees and going up to 100 degrees. So our final temperature is 100, and we started at 22. So that looks like that's about a 78 degree change, and that's a positive change, right? So remember, specific heat can be positive or negative, the temperature change can be positive or negative, and the energy change can be positive or negative, but the mass and the specific heat can never be negative. All right, so now all you're going to do is put in these numbers in your equation. So we have Q equals the specific heat, which is 4.184 joules per gram degree Celsius. And then we have a mass of 3,999 grams. And we have a temperature change of 78 degrees Celsius. So you can see your grams and degrees Celsius are going to cancel. And it's going to leave you with units of joules, which are the units of energy that we want. And if you plug that in your calculator, you get 13, very large number, 1305.081.6 joules. So you should be able to do a specific heat problem like that, kind of a straightforward one.